Okay, welcome everyone. So today's speaker is Alberto here, and he's going to talk about black hole entropy and EFT transitions.
Okay, so thank you. Thank you everyone for coming, and thank you for giving me the chance to present this, my most recent work actually, here. And I'm particularly excited to talk about this here because actually the original idea came while I was visiting last year. And of course it was completed once I started the project. I'm very excited. So you can see the topic or the ideas will revolve around black hole entropy and quantum corrections. And in particular, this talk will be based on this recent paper that I wrote in collaboration with Matteo Zatti, who is a postdoc at UNIC. And if time allows me, which I'm not super optimistic about, I will also try to tell you a little bit about things that we are currently thinking about, which build on this work here, together with Deluz, Carmine Montella, and Matteo as well. Okay. But before going directly into the meat, let me try to set up a little bit the stage to make sure that we're all on the same page, and also because it gives me kind of a good opportunity to give you the ideas that we're motivating, we're driving this work. So let me start by perhaps stating something that we all know, and we are very familiar with the fact that at low energies, and by this I mean for sure well below the Planck scale, gravitational interactions are well described and well accommodated by the framework of the effective field theory. This means that if you're given some matter or energy distribution, of course you can use Einstein equations, which we can get from here, to deduce what's going to be the space-time geometry background and vice versa. But the very fact that this framework is should be interpreted within the framework of effective quantum field theory means that sometimes we may be able to say something interesting about the metric fluctuation, the quantum fluctuation of the metric itself. And at least, very roughly, what we can say, or we could say like with confidence, is that this Einstein-Hilbert-Lagrangian here should be interpreted as just the first of an in-principle infinite series of higher derivative and higher curvature corrections, which typically are written in terms of some energy expansion, controlled by some cutoff, lambda QG, by which I will then refer to in this talk as the quantum gravity scale, beyond which quantum gravitational effects are unavoidable. You can no longer describe it in terms of some local EFT coupled to gravity and so on and so forth. You need to resort to some UV complete framework, like string theory or whatnot. So these are more or less the idea or the lore that has been floating around since, let's say, for instance, the 80s. But I should say that perhaps during the last couple of years or so, there has been a lot of efforts within the string theory community, and in particular within the Swampland context, to try to make this more precise and study systematically what kind of higher derivative corrections show up in gravitational EFTs in different dimensions with different amounts of supersymmetries and so on and so forth, obtained from string theory compactifications. So, and with this endeavor, what we wanted to understand is, precisely what kind of EFT expansion shows up, where here, ON are the higher derivative and curvature operators of the classical dimension n, with this kind of suppression with respect to Einstein-Hilbert and so on and so forth. And we've been able to, see this very explicitly at face value in a lot range of compactifications, and also to try to study what is this guy. So whether it is the naive guess that one would have expected, namely the Planck scale, or if it's something else, and it turned out to be something else. Namely the so-called species scale or quantum gravity scale, which is something that depends, of course, on which point in moduli space we're sitting at, so which backward we're looking at, and can even be parametrically lower sometimes than the Planck scale. So this is more or less the buffers, and there's a very nice story going on here. But of course, you may wonder at this point that building on our experience with quantum field theory, something that for sure we may expect is that even before reaching this super duper high energy scale, what we should expect is to hit some other typically lower massive scale where some massive degrees of freedom start, we start becoming sensitive to some massive degrees of freedoms that were not in our theory, therefore invalidating the EFT and so on and so forth. These kind of corrections typically also show up. So these kind of field theoretic corrections show up in the same kind of higher derivative expansion in gravity, but they do so in a very different way. They're typically controlled by this kind of power-like series, which is different than this one, suppressed by precisely the mass a scale associated to these degrees of freedom, let's say some finite amount of particles, or perhaps some even Kaluza-Klein towers. And the very fact that these two EFT expansions are different is nothing but a reflection on the two very different physics that they are associated to. For instance, this one typically comes from threshold effects to these massive states. So beyond this energy scale, of course, there's nothing wrong. We just have to integrate them in, perhaps the decompactification and experimentation, but for sure we can still, or typically we can still write down from local Lagrangian factor to gravity and so on, in contrast to what happens beyond this energy scale.
How are you distinguishing these two effects in the EFT?
So, I mean, if in the EFT, you mean like if you take an example, let's say string theory compactification, and you literally look at the higher derivative expansion, okay? Typically what we do to actually disentangle these two things is take some limit, like some extreme limit in moduli space, where these two scales become parametrically decoupled, and then you can tear them apart. So for instance, if I compactify my theory and on some volume and I make it large, then my as I'm going to tell you, my quantum gravity scale is typically the higher dimensional Planck scale. This gets parametrically lower than the lower dimensional Planck scale, and even parametrically lower, you find the KK scale. And the fact that you have these two very different power laws is something that you can see. So you typically have this.
But typically, there's a hierarchy in the sense that the second one is the last one is much more important.
Typically, yeah. It depends. Sometimes, naively, you would have expected this to be much more important. Sometimes, and for some observables, actually, this is the most important one, and this is something that I'm going to talk about today. So yeah. This, in principle, yeah. Before
the operators aren't always the same.
Sometimes within the same kind of operator, you can see the two things showing up. Sometimes there are some of them which are absent because of some supersymmetry argument, but typically, yeah, you can see both of them. Okay, and actually, studying these kind of things systematically, you can make nice connections with bootstrap, gravitational amplitude, and so on and so forth. So this is something that we also looked at in a very recent paper, but this is not going to be the topic for today. So the question that we're going to ask today is somewhat related but different one. Namely, we want to understand how genuinely gravitational objects, namely black holes, can know about this multi-scale structure of gravity. Okay, this is the kind of motivational question you wish. Of course, at this point, you may also say, well, we know a lot of things, right? And we can try to answer this question straight away. For instance, if we think about the simplest possible scenario, which is the one that I was flashing out a couple of minutes ago, which is take some T+1 dimensional field theory coupled to gravity, put in a circle, focus on the low energy regime, well below the KK scale. You do see these two kind of EFT expansions showing up where the higher dimensional Planck scale plays the role of the quantum gravity scale and the KK scale plays the role of the field theory scale. And within these kind of theories, if you start thinking about black holes, for instance, neutral structured black holes, which you can construct by taking some black string in the higher dimensional theory and wrapping up on a circle. If you take this very big black hole and let it evaporate so that it shrinks, at some point it will reach the length scale of the order of the KK scale, and there there's a mode that becomes tachyonic, it becomes stable. These configurations destabilizes, it breaks down into pieces, and presumably after the dust settles, it recombines and perhaps localizes into some higher dimensional black hole, which is the preferred style thermodynamic. So this is a way in which, and this of course was something that was actually done here. This is the well-known Gregory-Laffan transition or instability, and it's precisely a very physical way in which our black holes can know about this theoretic scale. What about the other one? Well, actually, by thinking about black holes, it was how this kind of species scale, if you wish, was originally introduced. So what I'm going to tell you is very heuristic, so be aware of that. But at least it gives you a flavor of the connection between black holes and the quantum gravity or the species scale. So imagine that we start again with our big black hole, we let it evaporate, let it be a Hawking radiation or whatever, so it shrinks. Imagine that for some reason it doesn't, get into any instability of the sort that I was telling you about before. So you can still let it evaporate and it shrinks. You can ask what is the minimum size of the semi-classical black hole that you can describe in your EFT. And it turns out that it's not of order Planckian. Essentially, because of entropy considerations, this becomes particularly clear if in your EFT you have a very large number of light species. In that case, if your smallest black hole is of order Planck, then the entropy is of order 1. And for sure, what you can do is throw your particles into the black hole, and it should account for that. So in principle, the entropy should be at least roughly speaking of order n, at least. This is a way in which you can actually motivate, higher length scales as the minimum semi-classically describable length scales in that. And precisely that length scale, it's the species scale. This is very heuristic. This is very roughly a very rough argument, but there are many other ways in which you can introduce it. But at least you can associate this scale as the minimum possible black hole size, if you wish, or controlling the minimum possible entropy. Okay. Good. So for today, the idea will be to try to check and study more specifically, more thoroughly these expectations, these heuristic expectations sometimes, in a very controlled setup where we can actually trust our solutions, our black hole solutions. They will be protected by supersymmetry. We're going to think about supersymmetric supergravity EFT, where I can tune the size of my black hole and keep track of what it's doing, what are the correct observables, how they behave, and so on and so forth, and see how these two scales show up in there. So this is more or less the idea. And the punchline, just in case you want a couple at this point, is that indeed, whenever my black hole, my BPS extremal black hole, reaches a size of the order of the field theory or KK scale in this case, the EFT can no longer provide a well-behaved quantum-corrected entropy, which is the object that we're going to study. It actually gives something that is completely non-sensible. Kind of diverges, it behaves very badly. But it's only after we really take into account all the non-localities associated to the extra dimension, so we decompactify our theory, resum all these corrections, where we see that there's nothing wrong. It's just that our local lower dimensional EFT can never correctly describe the physics associated to those black holes. And similarly, if you keep pushing and then make it smaller and smaller, the minimum size happens precisely when my black hole horizon reaches a size of the order of the quantum derived distribution. Okay, so our expectations are going to be borne out, but in perhaps a little bit more subtle way than before, than for neutral black holes. Okay, so as an outline, it's very simple. So we're going to review the machinery that we will need to discuss all these systems. And once we are equipped with all these tools, we're going to study two different systems, so two different families of black hole solutions, BPS black hole solutions, to make sure that we are not getting misled by some artifact due to one particular family of solutions, and see how these things show up in that. Okay? I will let you know after all later on what the systems will be and why we choose those. So good. Okay, so let's start with the review part, if you wish, like setting up a little bit the stage. So the theory is, so the laboratory that we're going to use is four-dimensional gravities obtained from string theory, preserving 8 supercharges. Okay, so there are many ways in which you can actually construct these theories, but certainly the one that I'm going to think about because it's very useful, and I will tell you why later on, is taking Type IIA string theory, put it on a Calabi or threefold, and then at low energy you're left with this kind of thing. Okay, so I will always be thinking in terms of Type IIA string theory compactifications. Now, what do we know about these theories? Well, at the two derivative level, everything is well known. We have in the bosonic action, we have the usual massless spin to field, so the graviton. We have a bunch of U1s, all of which, except for one, belong to vector multiplets. These vector multiplets contain not only this in the bosonic sector, these U1s in the bosonic sector, but also some scalar fields, some complex scalar fields. The sets here, which are exactly massless, of course, and whose kinematics is controlled by some nonlinear sigma models, so some metric GA. And besides, you have hypermultiplets. So in the bosonic sector, those contain a couple of complex scalars, and their metric or their kinetic terms are I'm summarizing in this term here. Okay. So one important feature about these theories is that thanks to the extended supersymmetry, of course, the blackness expectation values of these exactly massless scalars parameterize a different Bakwa, my theory. And this describes a moduli space, which is a very rich and geometrical object. And in this case, it factorizes locally. So you have two factors, right? The one related to the vector, multiplet sector, and the one due to the hypers. Now, everything that I'm going to tell you about in this talk, so my black hole solutions, the observables that I'm going to care about, and so on and so forth, are such that only depend on the vector multiplexer. So I can safely forget about the hypers, and I'm going to do so in what follows. So we're going to just truncate our theory to the spin 2 and spin 1 sector, if you wish, and of course the associated scalars. Good. So what do we know about the vector multiple sector? Well, the vector multiple moduli space geometric is very rich, as I was saying, like it describes a projective spatial manifold. So your kinetic terms are described in terms of geometric, which you can derive from usual from a Castello potential with supersymmetry. And this Castello potential is completely determined in terms of some holomorphic sections on the moduli space, so the periods. Thanks to the symplectic structure of this moduli space, I can actually choose some particular frame in which my coordinates themselves are nothing but like portions of this half of these periods, the x-axis. And the other half I can derive or can be derived from a single object which is holomorphic in the x-axis and homogeneous for the two, so the prepotential. So once you're given this guy, you can take derivatives, you can compute all the periods, therefore the metric, and even the gauge kinetic metrics, gauge kinetic function. So the guys that were showing up in the here, right? Both the kinetic terms and the theta. Good. Okay, but this is just at the two derivative level. And as I was saying at the beginning, we're gonna study the higher derivative structure of the theories. So it better be that we know something about these corrections in this kind of theories. And we do know a lot of things. So in particular, there's a special class of terms, of F terms. So they are protected by supersymmetry, which are higher derivative and higher curvature. And can be written in terms of superspace integrals like roughly like this in terms of these two superfields. So these ones depend on the vectors, and this is a very special, like the Bell superfield. Notice that there's infinitely many of those. Okay, you can actually, this has a very nice interpretation in terms of topological string theory and free energies and so on and so forth. So these terms, after you take the integration over the fermions, you can think of those as giving rise to local operators of this form, among others. Again, this gives you the kind of Wilson coefficients, which of course depends on the point moduli space you're sitting at. And it's higher derivative and higher curvature because it depends on the square of the anti-self-dual piece of the Riemann curvature and also the graviphoton field strength. So here you see that you have like a power-like series. I didn't tell you, but the graviphoton is a very particular combination, linear combination, depending on the moduli of the U1s that were shown up before, which belongs to the gravity model. So it's gravitation, it couples to the mass actually. And it enters into the supersymmetry variations of the Gaugino and the Dilatino and Gaugino and so on and so forth. Good.
Sorry. So by vector multiplet, do you mean the one that includes the graviton or the one that's just vector field, fermions, and scalar?
No, exactly. So this guy is the one that doesn't belong to those.
Okay.
Yeah. So this is what the one that enters also into the bosonic content of the gravity multiplet in 14 equals 2. The other ones are orthogonal. Okay, so the only one that shows in this kind of F terms is literally the graviphoton, so not the. Okay. So there are many other terms that you can think of these guys as associated to this kind of local operator. Good. What about the other piece of the story? So what about black holes? Can we construct black holes in this series? Of course we can. But not only that, since we have like a bunch of U1s, we can find extremal black hole solutions, so black holes which are charged under the U1s and preserve half of the supersymmetries. These objects have a line element that in general one is not able to write down, but so I will leave it like this. And you can think of those as solitonic objects which interpolate between flat mean cosket infinity, where you don't know almost about the black hole, and an ADS2 versus 2 maximal supersymmetric solution at the edge. Okay. And one of the very nice features about these black holes is that all the physical properties that we want to care about, the radius or size, the entropy, and so on, are completely determined in terms of the gauge charges. Once you know those, you can actually find out which are the properties of these black holes. And this follows from the very well-known attractor mechanism. Now, this mechanism was originally introduced at the two derivative level. And here we're going to care about the higher derivative corrections as well, the ones that I was telling you before. So it better be that we are able to do something like extend this formalism to also accommodate those. As it was derived, understood by essentially these people here, back in the late 90s, you can do that. So you can generalize your attractor mechanism to also include these F terms. And the equations are very similar to the ones that today. So if you're familiar with those, then what I'm going to tell you is going to be clear, hopefully. If not, it doesn't really matter. This is just a way to actually set up some algebraic equations which tell me from which I can derive all of my gravitational observables associated with black holes. So the entropy, the size, etc., etc. Okay, so these are the kind of equations that you have to solve, even when you have higher derivative corrections. So the attractor equations with this kind of generalized Lagrangian are very similar. So you just introduce scale variables via some compensator field. This is very similar to the 1 and 2 derivatives, but as you can see, there's an extra dependence on the graviphoton. And the reason is because while in the 2 derivative level, this would be kind of the other half of the period. So taking derivatives by the prepotential with respect to the x's, the xa's. In here, all these quantities are derived from a generalized prepotential, which is a formal power series, including the genus zero term, which is the usual prepotential, plus higher genus terms, which are nothing, as you can see, but are associated in a one-to-one way to the higher derivative corrections. So the coefficients actually, higher genus terms are literally proportional to the Wilson coefficients, if you wish. And W again is the graviphoton. Good. So in terms of these variables, the attractor equations are exactly the same. So they are usually given in terms of the magnetic and electric charges. And there's a rescaled version of the graviphoton. I didn't tell you about it, but it's not really important. It's the same kind of compensator-like structure. And in these theories, this guy is also said to be some constant. Okay, so this is the equation that one has to solve to find out everything about the black hole, BPS black. And from here, using Wald's formalism, you can find out also the entropy. It turns out being a very nice symplectic object. This is not really an entropy. I should say that it should be better regarded as an entropy index or something that is protected, kind of a gravitational index. And this is one of the reasons why we can't forget about the hypers. Everything that we're going to talk about, it's really insensitive to the hypermultiplet, to what happens in the hypermultiplet. Okay, so this is the formula that was derived.
Right. So when you actually go and compute this,
Yeah.
It's series expansion in that G.
So yes, exactly. So this is like a series expansion in G. Yeah, you insert it, but I mean we're gonna solve it in a moment for very specific black. Yeah, you should. So actually, your question. So everything that I told you is completely general. I haven't specified any particular prepotential, right? When you give me a specific model, you have to compute all these kind of corrections. And in principle, from this local 4-dimensional EFT, since they really come from local operators, it's really a power-like series. But we're going to see that this is not enough. And this is at the heart of one of the transitions that I'm going to talk about.
Sorry, and this G expansion is expansion in which? I missed that part.
So if you wish, it can be, think about an expansion in terms of the classical dimension of the operators, like here. You see, like as G grows, the dimension grows. It's 2G plus 2.
I see.
Or, but I call it G for a reason, because these terms can be computed. Is there like literally corrections to the topological free energy?
I see.
So it's literally the genus. That's why I chose G.
Right. So when you say is counting the classical dimension, is also accompanying some dimension for quantity, right?
Sorry, what? Can you repeat?
You said that it's for the classical dimension.
Yeah.
Then it's going to accompany different powers of some massive, like mass scale.
Yeah,
Which
completely.
scale? Like
Completely, yeah. So I mean, so here I think you're getting ahead, but I'm perfectly happy to answer that. So in principle, these guys are wild beasts. They have like many corrections. Now, when you think about how they show up in the setup that I'm going to tell you about, they typically come from threshold corrections due to some BPS states in M theory or M theory in the circle. So yeah, literally, the mass scales that are going to show up in there are the mass scales of these BPS objects. But a priori, you wouldn't know, right? I mean, and also from the perspective of topological string theory, you wouldn't know.
So I think you said before we can forget about hypermultiplet, but just now you said we shouldn't forget. Can you say again?
It's not that we shouldn't forget. So in principle, if you're computing an entropy, you shouldn't forget. I mean, they will know also about the background that you're putting your black hole in. The point is that this entropy was derived by taking the Lagrangian truncated to the spectrum that I was telling you, so vector plus graviton plus these F terms, which only depend on the vector multiplets. This is a world entropy coming from this truncated Lagrangian. The question that you may ask is, why should I trust this guy as a good observable, and not why I shouldn't include also the hypers, and whether the hypers are gonna modify this guy or not. And the point is that if you interpret this, you can see that this object is an index. So it's like a Witten index.
The preposition depends on the hypers, right? You
Potential
integrate
doesn't.
out,
Doesn't
the preposition depends on integrating out the charge type of model. It's the one loop correction,
I think you're thinking in terms of 5D, which I would agree.
sorry?
In 5 dimensions, if you integrate a hypermultiplet, it changes the
It's
quantum
the same
numbers.
one loop contribution.
No.
for the-
In 4 dimensions, it all depends on the vectors. Take the cup. So why would you say that it depends on the? I mean, it's really the usual one, like cubic plus linear plus all these corrections. It's like a tree level. So let me put it this way. If you think about type 2 string theory, the prepotential, it's everything that comes at tree level, so only depends on alpha prime, not on GS. GS in the hypers, the decouple, so it doesn't know about hypers. In 4 dimensions.
I mean, in 5D does
So
not,
maybe you think it could be that you have some hyper multiplets which are charged.
that's what I said. the
Okay,
charge
but
type.
it's not the massless hyper multiplets. Doesn't depend on the massless hyper multiplets. You may have
Yeah.
massive
I agree.
hypers. Yeah. Okay, then yeah.
So so the black hole formula here, is it insensitive to the non-BPS couplings? Or there's tons of couplings in this
Yeah.
action. Do they matter for this? Or?
So in principle, not. It hasn't been proved. So it's believed to be insensitive because there's this paper by Oguri-Ström and Bafa which argues that it's really the Lejeune transform of a gravitational path integral. It only depends on BP, like literally a Witten index. So it wouldn't depend on hyper. Now it's not proven. There are some papers by Samir, Murthy, and some other collaborators which were actually showing that for an infinite family of D terms, so not BPS, that you could write down in these kind of theories, they don't enter. They prove that, but it's not proven. It's expected, and there are many reasons to believe that. You have like also CFT arguments in terms of microscopic counting, but it's not proven.
Can you also remind me, what is the curly Y?
The curly.
There's two Ys, I don't know how to.
What is the curly Y?
Why
This
the
epsilon.
curly,
Yeah. It's like so. When you put a BPS black hole in the in the horizon, what happens is that it literally the scalars flow, and they flow to a value such that my black hole is only charged with respect to the graviphoton, so everything in the vector multiplets turn off in a sense. And
So
the bracket.
W was a two form in your previous slide.
Yeah, so this is this guy. So you contract it. It's like field strength square, also with respect to because it's transformed under region 2, but never mind. It's like this contracted with itself, which that's W squared. Yeah, like F wedge if you wish. It's W which.
Y is a scalar? Oh, is it-
Yeah, it's this one is it's a scalar, yeah. So yeah, this epsilon is like a rescale version, and it's forced by the Tractor equations to be some number. So it literally goes like this W squared goes like the inverse of this in the horizon. This is something that you can derive. People have derived. Okay. So as I was saying, like this was very general. So we want to connect with the string theory. We need to know what are the kind of couplings that have to show up in there. And instead of going to very general or the most general Calabi model, what I'm going to do is focus on a very simple point that is almost universal in all these Calabi compactifications, which is the large radius point, where all the cycles of my Calabi are large in string units. Simply because, first of all, it is simple yet rich enough to illustrate all the things that I was telling you about, and also because it allows me to, organize in a systematic way between classical plus quantum corrections and so on. So close to this point, the prepotential looks like this. You have the classical tree-level cubic coupling plus corrections. as you can see, everything is determined in terms of topological data of my Calabi. The linear term comes from the R squared term, so it's the genus one correction. These guys, you think about string theory, they come from constant maps from the wall sheet to the Calabi. And everything that I'm going to throw away it's due to wall sheet instances, okay? Because simply we're expanding around the last respondent, this is exponentially superior with respect to this one. So this captures the leading of the quantum corrections.
Wasn't there a term that depends on the Euler characteristic of the Calabi?
Yeah, it's here and in here, like it comes next literally. So yeah, so this constant map literally, again, it's depending on the topology, the Euler characteristic. And importantly, this one, it captures all these higher genus corrections, and it can be written, since it
So
comes.
that knows about the hypers.
Yeah.
Because it knows about.
Massive hypers, yeah, exactly. And you can write it down as this formal power series with some coefficients which grow factorially. So this is an asymptotic series, and some expansion coefficient which is nothing very illuminating. It depends on y0 and epsilon like this. So this comes from constant maps, and these are going to be the two guys that we're going to study in detail while constructing our black holes. Their effects. Okay, this is very well known. Good. So again, using this kind of approximation, you can write down the entropy for your black holes, and a very nice formula you can use for computing everything is this one, which don't pay too much attention. It's just something that we use thoroughly because it's just to handle. Okay. Is there any other question right now? This is essentially to set up the stage, to know what is the theory, the approximation, and the effects that we're going to keep track of.
I'm a little confused about your comment with less independent hypermodel as well. I guess now, I mean, it also depends on the neutral, right? So it depends on.
On the number, yes. On the topology, yes. It doesn't depend on the PEPs, if you wish. So it doesn't really matter whether I change my PEPs of the hyper. They are not back-reacted a priori by putting my black hole. Yeah. They don't depend on the PEPs. That's the precise statement. Okay, so let's go into the first example, which is possibly the simpler one, yet the most interesting one, I would say, in light of what I'm going to tell you. So you can construct BPS black holes thinking about Type IIA Calabi by taking bound states of DP branes, wrapping different like cycles in the Calabi. The simplest example that you can think of is by turning essentially everything except for this X-branch charge. Okay, why is this the simplest example and the one that we're going to tell about? Well, because the attractor equations get much greatly simplified, and also because it's the only one that can prove a very particular limit that we're going to see. So before seeing what the quantum corrections do to the observables associated to this family of black holes, I think it's a good idea to study or review the two derivative solution so that we have a feeling of what kind of things are happening there, and therefore afterwards come back and study these quantum effects. So two derivatives, as I was saying, the attractor equations are very simple. I'm not going to show it to you today. They are linear. Typically, they're quadratic. Here, they're linear, so you can solve them. The XAs look like this. They depend on the imaginary part, the complex quantities. The imaginary part depends on the D4 branch charge, and the real part on the D2 branch charge. And these DABs are simply topological data. The X0, it's given by this quotient of gauge charges that I'm going to call X0 for a reason, because it's going to play an important role in black holes. Okay, so as you can see, everything's completely determined by the charges, and then you can try to compute all the observables associated to the black hole. So the radius, the entropy, which are proportional at this level, and so on and so forth. Okay, this depends, as you can see, on gauge charges via this aggregate square root. Good. Now, what happens if I turn, well, before going to quantum corrections, actually, let me make a comment. So this solution is actually obtained by truncating to the cubic order in the prepotential. So I'm forgetting about higher derivative terms, of course. So just genus 0. But also I'm truncating to the cubic piece. Why? Or what was derived by truncating to the cubic piece? Why? Because a large volume, this is what dominates. And to make sure that this approximation is correct, and our solution really belongs to that, it better be that we ensure that all the volumes in the Calabi, which, as I was saying, they depend on which point in the space-time you are sitting at, are always large with respect to the string units. And the most problematic situation happens literally at the attractor lobe, so at the derivation. At the derivation, these scalars are such that the central charge of the black hole minimized. And you can compute there what are the different volumes and try to see how the large volume approximation translates into charge hierarchy. So growth of charges that we must impose so as to be sure that the solution is well under control and really belongs to the large volume. So after computing these things, you can, and after studying a little bit on this formula, you can get convince yourself that to have this large, you need these two quantities here, so D0 branch charge square and D4 branch charge square for every cycle to be much bigger than the x0 that I was telling you about before. But crucially, this x0 doesn't need to be specified. So it can be large, it can be small, it can be whatever. So at this level, we only need to ensure this to be true, which actually can be very easily solved. This is something that is very well understood by having my D0 branch charge much larger than the D4 branch charge. Okay, so this is the kind of charge hierarchy that we need to impose to make sure that the solution is really within the large volume region. When turning on the quantum corrections, the EYAs, so everything that is not the D0 branch charge equation, it's essentially the same, it's unchanged, you can solve it, it's literally, as you can see, it's literally the same solution. The only one that knows about the corrections, which are shown in gray here, is Y0. You can solve it in this implicit way, and I'm writing it like this because if you remember this G0, which is, well, G0 is like the derivative of G. G was the function which is like a formal power series on alpha, which is self-dependent or depends on Y0. So I cannot solve it explicitly. I can just only hope to be able to solve it iteratively under some sort of approximation and so on. But in principle, this is the solution. Good. So one question that you may ask at this point is, well, can we, find this quantum corrected solution as some sort of small deviation from the one at two derivatives? And if so, what kind of refined charge hierarchy should we impose? It turns out that you can actually do that. You can actually show how to literally find a solution which is very closely related to the previous one by asking for these two things. So if you remember before, we had to have D0 branch charge much larger than D4, but D4 could have been whatever. Now, also all the charges have to be large. And also, if you impose that this Q0 branch charge is greater than the extremized value, so once you substitute the solution of G0, then you can Taylor expand this equation and solve it order by order. And what you find at leading order is this kind of solution where Y0 you see is literally the previous solution minus some small correction, which is a small precisely because now we're asking the D4 branch charges to be big. This is due to the R-square correction. And also on top of that, you have an extra series expansion in terms of G0 over Q0. Good. So this is a way in which you can actually find a slightly deviated solution from the tree level one. And what I mean nicer, actually, if these two restrictions would have been translated very neatly in terms of refined charge hierarchies. This one certainly is this kind, but this one is not. So it's not very illuminating. It doesn't tell us what kind of physical condition I would impose here. But it turns out that by looking a little bit closer, you can find, literally what is the thing that we're asking. Of course, I didn't tell you, but from this kind of iterative solution, you can obtain the physics, so the observables, radius, the entropy with the correction, and so on and so forth. And this condition that I was saying, you can actually understand it by computing this guy in terms of the G series, with alpha being the expansion parameter. It turns out, believe me, once you study it more closely, that this condition, what asks is for the expansion parameter to be small, which means if you remember alpha is 1 over Y0, essentially, so it means that Y0, our solution, this one has to be large. Okay, if you have that restriction, you literally, this is a necessary and sufficient condition to have this. And what this translates at the end of the day is for the previously undetermined quantity, this x0, to be actually large. So you see that now, to really have a solution under control, which has some small quantum corrections with respect to the tree level one, you need your D0 branch charge to be larger than the D4, but not too large. It cannot grow like larger than cube order. This one. Okay, this ensures that your quantum corrections are well under control. Okay. Good. Why am I stressing this? Well, because at the same time, once you have understood what kind of restriction you have to impose, it gives you a handle or an angle to ask about what happens if you don't do that. What happens if your expansion parameter, this alpha, starts growing? which you can actually engineer very easily by literally rescaling how these charges grow. An intuition of what happens if you try to make this parameter large comes very easily by thinking again about the prepotential correction that was captured, or the dependent alpha. Here, the series, as I told you, these coefficients were growing factorially. This means that the series is asymptotic. It's asymptotic for alpha small. So if you engineer your solution to have this alpha parameter small, no matter how small, you can always include more and more terms. Well, actually, not infinitely many, no, but the smaller your parameter, the more terms you can include in this series, and therefore more accuracy you have to all these corrected quantities. Now, when alpha starts growing, what happens is that this series starts behaving extremely badly. So no matter how you truncated your series for some small alpha, if you start increasing it, at some point, they're gonna give you corrections which grow exponentially and cannot even or seemingly overcome the tree-level contributions. So they behave super badly. Put it another way, you can always study what is the optimal truncation of this series, and it turns out to depend on alpha like this. So for alpha order 1 or bigger, you're collapsed to the first term, and even if you truncate to that term, still you get non-sensible answers.
Can you remind alpha was?
Yeah.
derived or something?
Exactly. This is where I'm going. So in principle, alpha was literally the graviphoton over y0, which is something that doesn't tell you anything at first glance. What happens is that if you sit in the attractor locus that your black hole is forcing you to go to, it turns out that this alpha is nothing but the ratio of two scales, like literally the ratio of two scales. The M theory circle length scale and the radius of the horizon. It's literally that. And I'm literally, so R5, I'm calling literally the inverse of the D0 brane mass. So here with this observation, everything now becomes crystal clear, like qualitatively at least. So what is happening is that for alpha small, where I have all my corrections under control, my black hole, the radius of my black hole is super large compared to the M theory circle. So even at the horizon, the black hole doesn't know about the existence, or knows very little about the existence of the extra dimension and theory and so on. But if I start, changing my charges such that this alpha grows, at some point, when it becomes order 1, the two length scales are comparable to each other. Therefore, it's not surprising that our four-dimensional local EFT is not able to capture the physics associated to this kind of small black holes in a sense. Good, so this is a very qualitative understanding, but it would be better if we can make that quantitative. And this is what we're gonna do next. So the question I'm going to ask is, now that we know that close to the large boiling point, what is happening is that my M theory circle is growing, and I can engineer black holes of this kind, which actually become comparable of this size. The question is how my higher dimensional theory, which is well behaved, resolves this issue, how it cures this seemingly unphysical divergence on the entropy and so on and so forth. Okay, so this is the question that we're going to attack in the following. And the key to do that is to come back to the old work by Kobakumar and Bafa. The point is that, actually, as Minyo was asking, so in principle, this G, when you look at it from the four-dimensional perspective, is a series. It's literally like the series of higher derivative terms. But actually, in terms of, if you think about the topological free energy, it has an integral like Schwinger-like representation, from which you can, of course, derive the asymptotic series once you expand this, exchange the sum, and perform the integral. But in principle, this is more complete. This gives you the exact answer. What we have to do is come back at this, compute it for the D0 brane tower, which is literally the one responsible for the constant Mach contributions when seen from the M theory perspective, and see whether this can cure this problem. So it turns out that Kobakumar and Bafa already did the computation for us. This computation has two pieces, one which is perturbative and another one which is non-perturbative. In the following, I'm going to throw away this guy. I'm going to come back afterwards. And I'm going to focus on literally what Kobakumar and Bafa computed for the D0 branes. They computed much more things for D2, D0 bound states, and so on and so forth. For us, the leading order corrections are due to these constant maps, so they come from the KK tower from theory for D0 branes. So if you do that computation exactly, so not like approximating and so on and so forth, you find this expression here. This was already computed by GBS already. Now, crucially, this guy is well behaved for every value of alpha. So now nothing fancy happens at alpha order 1. It's perfectly well behaved. Importantly, is a non-analytic function of alpha equal to 0, which means that for alpha small, you can actually expand it. You have this asymptotic series, and the 4-dimensional description in terms of this series of corrections works perfectly well. But when alpha grows, and in particular when it grows a lot, it starts decreasing exponentially fast. Okay, and to actually see this, how this happens in the exact formula, you cannot write that down in terms of some series. It's really a non-local physics associated to the system of the full extra dimension. So it's not surprising that the 4-dimensional EFT could never see that precisely when you cross this kind of transition region. Good. Now you can redo the exercise, compute the entropy, the sizes, and so on and so forth, and everything can be written in this slightly ugly formula. Of course, alpha and y0 should be taken as the exact solution for the tractor equation. But this formula in principle is very well behaved for every value of alpha. There's nothing fancy or anything going on. It's really a 5-dimensional computation in disguise, okay, which is well. Now, interesting thing about this formula. So I told you that the small values of alpha were actually taming all these corrections. They were controlled, subleading, blah, blah. When alpha becomes order 1, then you start getting problems if you insist on using the 4-dimensional perspective. But I told you that by choosing wisely your charges, you can actually also even cross that point. So you can make alpha grow very large and explore this kind of tail of the function. So the question is, what happens there? Well, if we come back at the interpretation of alpha large means that now my black hole becomes smaller, parametrically smaller than the size of the extra dimension. So what I'm starting to see, but I didn't tell you, but these black holes actually are very reminiscent of the Gregory-Laflamme ones in a sense. They are 5D black strings which you put on the circle. So if I try to, this is the reason why you can actually take the large alpha region. If you insist on taking this limit, you start focusing on a region closer and closer. My transverse horizon gets smaller and smaller compared to the full size of the circle. And at some point you have focused so much that essentially what you're left with is an infinitely extended black string in 5 dimensions, which is not really infinitely extended because ultimately the volume is regularized in the IR by putting it on the circle, a very large circle. So in a sense, this limit is probing a very deep 5-dimensional UV regime, that of a black string. So the question now we can ask now is, does our formula, the ugly one I was showing to you here, really capture that the physics that we were expecting according to this picture? So what happens if if I take alpha big? Here, more or less, you can really see what is happening. So everything's literally exponentially suppressed, and the only thing that survives is this term here. Okay. So the picture, well, just as a summary, this is the complete picture for this kind of system of black holes. Alpha small is a big fat black hole in 4 dimensions. Alpha, or the one that starts knowing and being sensitive to the KK scale, and alpha large is literally the infinitely extended black string. Now, when we take the alpha large limit, this is the entropy that we are left with. Maybe for those who are familiar, you may already recognize it, but it's nothing but literally the IR regulated entropy of the, even quantum corrected, of the 5D black string. I say regulated because, I mean, strictly speaking, an infinitely extended black string will have a finite density, entropy density. So what I'm getting is literally the quantum corrected entropy density regularized by putting it on a very large circle of size given precisely by the empty circle. And this you can actually match with many computations. For instance, the microscopic or the original microscopic computation give you this. This computation is exact precisely at this point. You're not missing anything else.
So which high derivative? So this is including nothing beyond the F0 or what's
No, actually, yeah. So what happens? So in 5 dimensions, when you try to lift all these kind of terms that I was telling you, so the 2 derivative plus higher, there's only one that survives and that exists as a BPS operator in 5 dimensions, which is the R squared term.
the R squared term?
G equals 1. So this one is the G equals 1 correction. This is why I say that it's quantum corrected, because this will be the classical entropy of the black string. This contains also the effect of the R squared. So and this is like literally matches the microscopic computation and some macroscopic computations that you can actually do in 5 dimensions, where you take you use holographic methods, the ADS3 throw that you have in the black string and so on and so forth. So this way you can actually claim and say how your macroscopic 4-dimensional entropy matches all the way to the UV1. And you can see how all these thresholds disappear, get diluted, and so on. Also, relatedly, we can try to answer one of the questions I was posing at the beginning, which is, well, since we have already crossed the KK threshold, what is the minimum size that we can make our black string to normal? So what is the minimum entropy, for instance? Now, to really be in this kind of regime, we still need to have this guy very large, so a very large circle, and a small horizon. And therefore, we minimize the entropy by literally minimizing this guy here, which happens for brane charges of order 1. In that case, you see that these two terms, so tree-level Bekenstein-Hawking plus the quantum correction, become of the same order. So the quantum gravity expansion, it's literally breaking down. And and literally the entropy that you get is nothing but the quantum gravity one. So the one controlled by the species scale, if you wish, which is the 5-dimensional Planck scale, and so on and so forth. So this is a very precise setup, very well-controlled setup in which you can really keep track of what the black hole is going and you shrink it. It knows about the KK scale because the 4-dimensional EFT quantum corrections to the entropy behave very badly. Once you decompactify, you resum all these corrections, they dilute. You can keep going and make it as small as the species scale. So this is the example in which you can see all these things happening at once. And this is why this system is very good as well. Good. Some other interesting stuff. I told you that the Gopakumara alpha computation actually has an extra piece. So, this can be motivated from many perspectives. If you think about the GV computation as a swinger lag computation, we know that there are pair production effects. So one may wonder what happens with those. Can we take them into account? Can we do the ES-Pod our analysis? You saw that this matching was very sensitive to us being able to dilute away all the corrections except for the ones that actually appear in the microscopic computation. So anything else that you add is going to spoil the matching for sure. Also from the topological string theory perspective, this prepotential is nothing but the free energy. And we know that this comes perturbatively, so there are non-perturbative effects which could enter there and could modify our analysis. So the question is, are we getting misled, or all these things are gonna disappear when we take into account the effects or not? Okay. So to answer that question, we come back to the GV computation. And we have to be slightly more careful. So when we were computing the corrections due to the D0 range originally in the GV well, it was later understood by Ed and Dushenko, that by Whitman and Dushenko, that actually this computation, the way in which it is holomorphic is slightly tricky. It happens because your mass is non-holomorphic, it enters into the exponential, like the usual swinger-like suppression. But the coupling to the graviphoton is actually anti-holomorphic. So if you want to reproduce the GV computation from the top down, what one has to do is to redefine the integration variable to take away the anti-holomorphic dependence. Here you cannot see whether it's holomorphic or anti-holomorphic, but believe me, if you consider D2-D0 brane bound states, you see that how these things go. But the point is that you have to change variables. That way, holomorphicity is completely manifest. Now, if you try to change variables for positively charged D0 range, everything's fine. You have to take S goes to S over 1 2 pi n. So, sorry, S goes to S over 2 pi n, which is fine. It just takes away this n here. It leaves you with the Gopakumara alpha computation, and that's fine. And the integration ray, it's left untouched. But for the negatively charged D0 range, actually there's a subtlety, because when you try to do that, to actually do the Poisson resumation and find the result, you find that you certainly take out this n here, but since n is negative, now your integration ray it's actually along the negative real axis. To reproduce the GV computation, what you need to do is to have the two rays coinciding. That way you can use Poisson resumation and find the exact result. So what we need to do is to take the negative, one of those, and then deform into the other. Good. This would have been at free of cost if there's no pose in the integral. And of course, provided, you know, the arc at infinity doesn't contribute. There, at infinity doesn't contribute, but certainly there are non-perturbative poles, like in the usual Schwinger computation, which are, you know, along the imaginary axis due to this hyperbolic sign. Well, actually this one. So what happens is that when trying to deform the contour, apart from the, you know, perturbative correction that you get once you have deformed it and resum it, you get non-perturbative contributions due to these residues. And these are exactly the non-perturbative corrections to the topological free energy or the non-perturbative corrections to the D0 brane per production in a sense. You can compute those like as I was telling you, like carefully keeping track of the integration domains and then deform it, or you can not deform them, like literally resum them, slightly varying, deforming a little bit the contours, resum it, and write down some integral which is democratic in a sense. And I say democratic because literally the poles, so you have two kind of poles, ones which reproduce the perturbative piece, and other ones which reproduce the non-perturbative piece. This formula, I should say, that was also derived the same time by these people here. I think they are more general because in principle they claim to have it exact formula also for including D2 branes. Here we were only caring about D0 branes because they give you the leading on the corrections, but I should also point out that this other reference arrives at this formula. Okay. But regardless of which one we use, this is the result that we get. Okay. You have like two terms, the two polylogarithm terms. For small values of alpha, you get like the usual exponential suppression, very familiar from Schwinger, like it's literally the same as in flat space. So they are well under control. But the problematic, something problematic happens when you try to go at large values of alpha. So precisely in the regime where we were able to match the entropy.
So with this calculation at small alpha, do you get back precisely the right D0 brane contributions?
The point is that this is the exact D0 brane contribution.
Exactly.
This is the exact one. What I'm saying is that for small values of alpha, you get the typical intuition of what happens in flat space. So e to the literally to minus 4 pi square over alpha over GS if you wish. Yeah. But for large A, this grows in a polynomial way, so cubic. And this should make us nervous because, as I was saying, like the matching was very, very sensitive to us being able to throw away or everything else diluting except for the guys that actually match the microscopic computation. And this seems to certainly not be diluted. Actually, it grows.
I still got myself confused. Which quantum correction exactly is this? So this is pair producing D0 branes?
So this is very, very tricky. So it's not per production per se. I thought it was per production at the beginning, but actually you can have proven that you don't have per production of BPS states.
Yeah, okay.
Because the ADS2 crosses 2 if you wish is supersymmetric and is stable. So there's no discharge per se.
Okay.
The only thing that can happen is that you have non-perturbative effects can contribute to the entropy or not. These non-perturbative effects due to the D0 branes is what we are computing here. For the black hole, this is the black hole interpretation. If you go to the topological string theory perspective, this would be like the leading order non-perturbative effects in GS.
In GS.
Yeah.
So coming from D0 branes in type IIA.
Yes. Exactly. Anything else is suppressed with respect to these ones. Also go like 1 over alpha or 1 over GS, that they have an extra damping in the volume.
What is it? I mean, I usually think of these things as some kind of instantaneous configuration.
Yeah.
Right.
It's literally that, yeah.
But what is the D0 brane wrapping? Well, I mean, what is it? What is the word line supposed to be?
So the word lines, you can think of those as,
This is type IIA, right?
this is type IIA. They are closed word lines. You can think of those as closed word lines in the ADS2 crosses 2 background.
I see. So in that background. You can
Yes.
get something.
This is something under investigation because it's very.
Oh.
This is something that you don't see from here because you see. I mean, what you are doing here is take the. If you wish, you have integrated out the particles. You capture that in terms of the prepotential, and then you're looking at the back-reacted solution. So it's not that you're looking at what the particles do in the black hole background classical, but actually you're looking at the back-reacted solution.
Which captures the.
Yes,
the effects
yes,
of the-
exactly, yeah. But a rough way, or at least how I see it, is literally you are close to this 2 versus 2, you pair produce the D0 branes, they never escape, actually. The idea is to float. And they can give rise to corrections or not. So the question is whether they are giving rise to corrections. If they are, for sure they're going to spoil our result, our matching. And actually the point is that if you come back to you see there's a funny phase difference here with respect to the perturbative piece. Well, maybe you don't remember, but my time's up, so I'm gonna rush a little bit and tell you like summarizing some of the other stuff, but this is important. So the point is that when you do the computation, there's a like in Schwinger, when you compute the Lagrange, there's an extra I factor. This changes the phase of this correction. And it turns out that when you come back to the attractor equations and the observables, everything in the black hole depends only on the imaginary phase of G. This I factor this I factor together with this one gives rise to a real contribution. Okay? So it turns out that even though these corrections to the free energy are there, they never enter into any of the black hole observables. So our black hole doesn't really know about those. They don't spoil the matching and so on. This is a very nice feature and non-trivial check. So just to be a little bit fast, complete. Of course, everything that I told you was happening in a very particular system of black holes. We were able to see all these features, but you may wonder, was this an artifact of one particular family? Can we see similar things in other black hole solutions or not? So to answer that question, what we did was study the second to simplest example that one can think of, which is complementary in a very precise sense with respect to the other one, and see whether the same kind of things were happening. So these solutions are the simplest ones in which you include these brane charts. Okay, we turn off anything else, so we turn off D0 brane and D4 brane charges. The attractor equations are more difficult, they are typically quadratic. Turning off these charges literally makes now your XAs are real, before they were complex. And before X0 was exactly real, now it's purely imaginary. This is a sense in which the two are complementary, because they are kind of electromagnetic duals of each other in a very precise sense. The thing you're left with is to solve this kind of quadratic equation for the values of the x's. You can write it down in a better way. Doesn't matter. It depends only on the charges and the topology. It's not ensured that you can actually solve this. I mean, you have to choose your Calabi, put your topological data, and see whether with some charge choices you can actually find a solution. But if you are able to find a solution, then you can also engineer to have families of solutions by rescaling the charges. Okay. So you can engineer solutions which have some values, some vector of x, you can rescale that. You can compute the black hole observables, they depend on, of course, on the solutions, central charge, the volume. Again, you can ask what kind of charge hierarchy you have to impose to be on a large volume. It requires the D2 brane charge to be much bigger than the D6 brane charge. But similarly to what happened before, remember there was some particular combination which wasn't left untouched. It didn't need to be specified at cubic order. Here, the thing that you don't need to specify is the D6 brane charge. But again, once we turn on the quantum corrections, we will have to actually say something about this. You can compute the entropy and so on and so forth. Taking into account quantum corrections is a little bit more subtle here. It turns out that, again, you have a slight modification of this quadratic equation. Setting the D0 brane charge to 0, before, if you remember, essentially what you do is take Y0 to be purely imaginary, because you take that to 0 and then you have a solution. Here, even if you take out this term, this one is a little bit problematic. And it turns out that if you look at how this function, this G0, what this looks like when Y0 is purely imaginary, it turns out to be purely real. So now it's an alternating series. Before it was non-alternating, now it's alternating, and it's real. So again, this is exactly 0, so your solution is also consistent with quantum corrections. You can compute everything else, like back reacted or quantum corrected radius, the quantum corrected entropy, and so on. They, of course, depend on this formal power series of corrections from the 4D perspective. Again, you can ask whether, which by the way, I think I didn't say, but to have this alpha small and therefore under control, since it's 1 over y0, what you need to have here is largely zero brain charge. So again, having control over quantum predictions means that here you should have to put a much bigger than 1. But the important point is that you can also engineer situations where alpha becomes of order 1. So your solution is not very well captured by the for the EFT. Again, the modulus of alpha is literally the ratio of the two scales that you can prove regardless of your black hole. The one important feature about these solutions is that once you turn on the D6 brain charge, something very funny happens. You can no longer purify the regime where alpha grows as much as you want. And the reason is because of this charge quantization of D6 brain. This is the example that actually gets the highest alpha when you have, of course, D6 brain charge. So since this has a minimum, which is 1, the maximum alpha you can get is 2. So you can never, so it's crucial to really probe the uplift. You really need alpha to be exactly real. There's a very geometrical way to understand this. In terms of 5D theory, before we had like a black string wrapped on the circle. Here, black holes are 5D black holes at the center of a dot knot. And what happens with a dot knot is that even though the asymptotic radius is whatever it is, when you get close to the horizon, this circle becomes an angle of an S3 together with the S2 of the horizon. And therefore, here what happens is that you cannot decouple the two of them. At most, they can become of the same order. So there's a very, you can prove it mathematically, but the intuition is this one. This is why these black holes can never, ever cross into the 5D region. You wish you need to put the tau knot, you cannot simply uplift it. So the horizon is not transverse to the circle. This is what I'm trying to say. So again, you can find that you can take the order 1 limit for alpha. You see that this regularization, and therefore you need to explain why in M-theory terms everything is well behaved. This case is very interesting because since alpha is imaginary, actually what happens is that the poles now are completely rotated. So you can perform the computation, deform the contour without picking ever any poles. So you don't get any non-perturbative correction due to D0 brains in the free energy. And you find some, not close expression, but it's an integral that if you solve numerically, again, it leaves you a very perfectly well-behaved dependence for all the quantities. No? So not only the prepotential, but also entropy, etc., etc. So you no longer find any problem when alpha becomes of order 1. Perfectly well-behaved. And let me insist on the fact that the non-perturbative effects really disappear in this case. And the reason is, you can understand that in two ways. One is because the series of corrections in here, as I told you, now are alternating. If you try to use resurgent techniques, you will find that this means that the series is Borel summable. So you don't need to, there's no non-perturbative ambiguity. So in principle, you don't need those. But actually, by doing the computation, you see that they are not there. And the reason why they are not there is because this system, as I told you, it's kind of the electromagnetic dual of the previous one. The previous one, in a very precise sense, you can understand as a purely electric black hole, in the sense of my D0 brain in that background, it's purely electric. In this case, it's purely magnetic. As is well known, purely magnetic backgrounds never reproduce or never give rise to non-perturbative effects. Yeah, I know that I'm going a little bit fast, but just in case, I wanted to flash out these kind of comments because they're interesting. Okay, we also discussed some problems that arise with this alternative prescription. So it's actually not really valid for all values of alpha. It actually breaks down in the D2-D6. So when alpha is imaginary, this is the prescription I told you that these other people proposed. So in our opinion, this is not fully general. You have to be slightly more careful. The other one to work. So that's something that at least you can trust. And yeah, and just to summarize, we've been able to kind of show in a very particular setup how this multi-scale structure of gravity is probed by extremal black holes. It's happening in a very subtle way, in a sense. First, because the EFT stops giving reasonable and sensible predictions for black hole observables, for instance, entropy. Also, it really matches the intuition of my quantum gravity scale really controls the smallest possible semi-classical black hole that I can have. And we studied that by, looking at two complementary and orthogonal, in a sense, black hole solutions that nevertheless show up, exhibited the same kind of behavior. So we're confident that the things that we're observing are not artifacts of just one particular setup. And things that we can try to do based on this is going beyond large volume, of course, trying to include the Gaussian instantons, exploring other kind of singularities where you can match or try to match the entropy from 4D to perhaps higher dimensions, like in 6D. Also, it's important to understand what is the fate of non-perturbative effects in the general case. In this case, due to the D0 brane. So what happens? Do they didn't show up in these two examples because of different reasons. Do we need those to be in the general case or not? This also is related to the GB computation in AES 2 to really understand what these effects are, because they are certainly not per production. They don't make the black hole unstable. And at most, they can contribute to the entropy. So these are things that we're currently thinking about, and some of which are close to the published. So yeah, thank you so much. I'm sorry for being. Yeah, perfect.
I have one question first. Okay, because I forgot, but the Euler characteristic, when it's 0, all these corrections disappear.
Yeah, we are assuming that
So
it's not
there's
zero.
nothing to say there.
Yeah, you can, certainly there are cases in which these effects are, so one example in which these effects are not there is for Euler characteristic 0 Calabi. If you increase the supersymmetry, also these effects, or some of these effects go away. So with n equal to 4, you wouldn't see those.
Another thing about the MKK, technically that scale also exists in field theory. Like, I mean, you can have like 5D or some quantum field theory that in the UV become quantifies. So there should be some like observables that are not gravitational. That follow that scale.
So this scale, this is why, so the two EFT expansions are literally different because of that. One is field theoretic, it happens without gravity. Certainly, when you have gravity, it also affects gravitational observables, but not necessarily that, not only those.
But I thought the way you see, maybe actually I haven't followed much of that, but the way you see it isn't related to the black hole scale, which is inverse to MKK.
Yeah, so in the black holes know about that scale in this way, but there are other observables, amplitudes, that also know, because you have unitarity cuts. You need to.
That's what I mean.
It's But one thing that I find particularly interesting is that if you talk to UFT people, typically they will tell you, why should I care about the species scale if it's much higher than field theory scale? So everything that happens at field theory level, I would see way before, right? Something that I find interesting is that if you add gravity into the game, some observables actually tell you or are controlled, the corrections to those are controlled by the species and not the things. This is one, the entropy is one of those. So even though that scale happens way before, way below, and there are many other effects that you would see, if you start thinking about black holes, observables, and for some reason you have precision enough to try to deduce corrections to the entropy, what you would see is the quantum gravity suppression, not the other one, which is a little bit counterintuitive thing. I mean, it has to do, of course, with the UV-IR mixing.
So like comment. I mean, I think like the mindset is that when you compute this black hole entropy, you're kind of assuming you're in the origin of the hypermoduli space. Because if I Higgs it, like if I turn on a VEV, it's like doing complex structure deformation, and actually your entropy changes because of background change. So in principle, it does depend. It's not.
Yes.
Yeah.
So, but you are saying,
It's just like, I think what you're writing down is not that it doesn't depend in the hypermultimoduli space, is that you're at the origin of the hypermoduli.
yes. So actually, what you're saying, all this computation is carried out exactly when my hypers charged under the vectors are massive. That's the.
No, but I'm just saying, like, it's not that it doesn't depend on the things.
I agree.
Because even in your neutral ones, like I can go somewhere in the modular space that become charged, right? It's like unhiggsing the quintic or something, right? So I'm just saying these are allowed, and it would change your.
But those kind of transitions are. These are captured by the topological free energy, because typically they are
It's a different phase.
It's a different
You have to
phase, yeah,
compute a
your
different phase.
topological data changes and so on.
Yeah, so everything changes. So
No, completely, agree. Okay, so yeah.
So I would say that there is implicit, implicit, you're
Yes,
actually
yes.
assuming you're at the
I,
center.
it was more like, because typically, one objection that you could raise before even going to that, it's, do my massless in that phase, do my observable depend on the BEPs on the hypers? I can tune them, in my black hole.
Well, technically, yeah, they do. It's like a,
But I think
information.
to actually cross the two different phases, you have to move into the vector where some hyper becomes massless, changes the, it's like I can move for instance in GS freely and everything, nothing's gonna change. That's the claim. So yeah, I mean, there's definitely hyper effects. It's just not
it's
No, but
just the comment about
you're
being
completely right. And
independent, so-
actually, when you move in this moduli space and you hit one of these points in which you restore and clicks it or whatever, typically what you see is some kind of bad behavior for the entropy, similar to the KK scale, but only due to one hyper or finite amount of those. Something similar should happen as well there. Yeah. And this is why this, as you're saying, like these KK effects are not gravitational. You know, same kind of philosophy will happen for massive hyper becoming massive. Yeah.
I wonder even in QFC whether there's another cutoff or not. Like, is it like, what is the cutoff? I mean, there should be actually another cutoff of your EFT breaking down. Because there are theories that would include like strings or non-local stuff.
Yeah.
So there has to be an equivalent, I'm just saying, even of species scale that is non-gravitational. So,
Probably, I mean, in non-local QFTs, like, the ones that come from 6D and so on.
I mean, all the UV
There.
components, it is,
No,
I think
yeah,
we
yeah,
know are of
I
that
agree.
form,
I
actually.
agree. I mean, even in QED, you know that you have the strong coupling, which is very, I don't know, what is the order? of
No, but in
magnitude.
those cases, I actually know what kind of derivative become light, what kind of things you need to have it, so I'm not entirely sure how much like.
Yeah.
Also species scale is entirely gravitational sometimes, but anyways. It's about like,
It's certainly.
I don't think somebody has studied it like in that context, but there's definitely also a scale that is moduli dependent, even in quantum field theory, that tells you when this breaks down.
A bit of a naive question, and maybe you've answered this already, but do you have a picture of why your the result holds only in a certain charge hierarchy? Like, why do you require, like, what's happening when you take D0 charge being much larger than D4 charge?
So let me see if I understand what you're saying, or what you're asking. So the qualitative understanding of why I have to take the charge hierarchies as I do is literally this picture. So if I take D0 brane charge much bigger than D4 brane charge, but the D4 brane charge doesn't touch, it's order 1, or maybe it grows larger, but not too large, like not too fast, like not like PQ or something. Then the picture is that my black hole is very, very fast, very big. It doesn't know about the extra. If I now start playing with the hierarchies, what I'm doing is playing with the relative sizes at the horizon, which is where everything collapses to. So yeah, so this is like if you wish, the charge hierarchies are secretly here. How you change, of course, there's a common feature that is I'm still asking for my black hole to be a large volume. You can understand by asking D0 brane charge to be always very large. That's why I was playing with D4 brane charge.
Because these are BPS, you're changing the mass by changing the charge.
Exactly. Yeah. Exactly. Literally, by changing the charges, what happens is that my moduli at the horizon start moving, so they get to different points, which back react on the masses of the different objects, which you can visualize like this, right? Like the mass of the D0, it's literally the inverse of this size. So as I play around with the charge hierarchy, what I do secretly is, it's not that you can disentangle how the black hole radius and the M theory circle behave. Playing with the two are entangled, what I'm doing is literally playing with the relative sizes. So making them big, small, compared to each other, and
If there are no more questions, let's thank Alberto again.
You want to stop the record?
We can go.